I am Professor Sri. Welcome to the session on aircraft stability and control. If you want to know more about flight vehicle design, subscribe to the channel. So this session, aircraft stability and control. So here we'll be discussing about introduction, static and dynamic stability, coordinate systems, stability and control analysis, longitudinal moment, pitching moment, static pitch stability, and then static lateral directional stability, then aileron sizing, the concept of stick free stability, effects of flexibility, dynamic stability and its characteristics. So during early conceptual design, the requirements for good stability, control and handling qualities are addressed through the use of tail volume coefficients and through location of the aircraft center of gravity at some percent of the wing mean aerodynamic chord, as you all know, Mach. In larger aircraft companies like Boeing, Airbus, the aircraft is analyzed by the control experts, probably using a 6 degree of freedom aircraft dynamics computer program to determine the required center of gravity location and the sizes of the tails and control surfaces. An understanding of the important stability and control design parameters can be attained through study of simpler methods, which are also suitable for use by home builders and designers at smaller companies. This session introduces the key concepts and equations for stability control. These are based upon classical control methods, many of which were developed by National Advisory Committee for Aeronautics (NACA) USA in the period around 1925 to 45. Basic concept of stability is simply that a stable aircraft, when disturbed, tends to return by itself to its original state. Static stability is present if the forces created by the disturbed state push in the correct direction to return the aircraft to its original state. If these restoring forces are too strong, the aircraft will overshoot the original state and will oscillate with greater and greater amplitude until it goes completely out of control. Although static stability is present, the aircraft does not have dynamic stability. Dynamic stability is present if the dynamic motions of the aircraft will eventually return to the aircraft to its original state. Now, the manner in which the aircraft returns to its original state depends upon the restoring forces, mass distribution, and damping forces. Damping forces slow the restoring rates. Let us take an example of a pendulum swinging in the air, which is lightly damped and will oscillate back and forth for many minutes. Same pendulum, when immersed in water, are highly damped and will slowly return to vertical with little or no oscillation. Aircraft static and dynamic stability. So the figure illustrates the static and dynamic stability concepts for an aircraft disturbed in pitch. So let's discuss each by each nature of graph. So in figure A, the aircraft has perfectly neutral stability and simply remains at whatever pitch angle the disturbance produces. While some aerobatic aircraft are nearly neutral in stability, a few pilots would care to fly such an aircraft on a long trip in gusty conditions. Figure B shows the static instability. The forces produced by the greater pitch angle actually cause the pitch angle to further increase. Pitch up is an example of this. In figure C, the aircraft shows static stability with very high damping. The aircraft slowly returns to the original pitch angle without any overshoot. Illustrating figure D, which shows a more typical aircraft response. The aircraft returns to its original state but experiences some converging oscillation. This is acceptable behavior provided the time to converge is short. Figure E illustrates the restoring forces which are in the right direction, so the aircraft is statically stable. However, the restoring forces are high and damping forces are relatively low. So the aircraft overshoots the original pitch angle by a negative amount, greater than the pitch angle produced by the disturbance. Restoring forces then push the nose back up, overshoot by an even greater amount. The pitch oscillations continue to increase in amplitude until the aircraft diverges into an uncontrolled flight mode. Note that dynamic instability is not always unacceptable, provided that it occurs slowly. Most aircraft have at least one dynamic instability mode, the spiral divergence. This divergence mode is so slow that the pilot has plenty of time to make the minor roll correction required to prevent it. In fact, pilots are generally unaware of the existence of the spiral divergence mode because the minor corrections required are no greater than roll corrections required for gusts. Dynamic stability analysis is complex and requires computer programs for any degree of accuracy. So these are some of the nature of graphs we have discussed: perfectly neutral stability, static instability, static stability with very high damping, static stability with light damping, statically stable with low damping forces. Next, coordinate systems. So coordinate systems mainly it has two axis systems. One body axis system, second one wind axis system. So the figure of two axis system defines commonly used in aircraft analysis. The body axis system is rigidly fixed to the aircraft with the x-axis aligned with the fuselage and z-axis upward. The origin is usually at the nose. The body axis system is more neutral for most people but suffers from variation of the direction of lift and drag with angle of attack. The wind axis system solves this problem by orienting the x-axis into the relative wind regardless of aircraft's angle of attack or side slip. The aircraft is not fixed to the axis system, so the axis projections of various lengths such as the distance from the wing mac to the tail will vary from different angles of attack or side slip. This variation in moment arms is usually ignored in stability analysis since the angles are usually small. The stability axis system commonly used in stability and control analysis is a compromise between these two. The x-axis is aligned at the aircraft angle of attack as in the wind axis system, but is not offset to the yaw angle. Directions of x, y and z are as in the wind axis system. Longitudinal static stability and control. So before this concept, stability and control analysis, most aircraft being symmetrical about the center line, moderate changes in the angle of attack will have little or no influence upon the yaw and roll. So this permits the stability and control analysis to be divided into longitudinal and lateral directional analysis. So longitudinal involves with only pitch and lateral directional analysis involves with roll and yaw. So pitching moment equation and trim. So longitudinal moments. So this figure shows the major contributor to aircraft pitching moment about the center of gravity, including the wing, tail, fuselage and engine contributions. The wing pitching moment contribution includes the lift through the wing aerodynamic center and the wing moment about the aerodynamic center. Another wing moment term is the change in pitch moment due to flap deflection. Flap deflection also influences the wing lift, adding to that term. Flap deflection has large effect upon downwash at the tail. On the other hand, the long moment arm of the tail times its lift produces a very large moment that is used to trim and control the aircraft. While this figure shows tail lift upward under many conditions, the tail lift will be downward to counteract the wing pitching moment. A canard aircraft has a negative tail moment arm. The aircraft fuselage and nacelles produce pitching moments that are difficult to estimate without wind tunnel data. These moments are influenced by the upwash and downwash produced by the wing. So the engine produces three contributions to pitching moment. First one, the thrust times its vertical distance from the center of gravity. Second one, the vertical force Fp produced at the propeller disc or inlet face due to the turning of the free stream airflow. Third one, the prop wash or jet induced flow field will influence the effective angle of attack of the tail and possibly the wing. So the moment equation is given by mcg, that is moment at the center of gravity, that's equal to L into xcg minus xacw plus mw plus mw delta f into delta f plus mass of the moment of the fuselage minus LH into xr minus xcg minus tz1 plus fp into xcg minus xp. For a static trim condition, the total pitch moment must be equal to 0. This produces a term representing the ratio between the dynamic pressure at the tail and the free stream dynamic pressure, that is eta h is equal to qh by q. Static pitch stability. For static stability to be present, Any change in angle of attack must generate moments which oppose the change. In other words, the derivative of pitching moment with respect to angle of attack must be negative. The magnitude of the pitching moment derivative changes with center of gravity location. For any aircraft, there is a center of gravity location that provides no change in pitching moment as angle of attack is varied. This airplane aerodynamic center or neutral point XNP represents neutral stability and is the most aft center of gravity location before the aircraft becomes unstable. If the center of gravity is ahead of the neutral point, the pitching moment derivative is negative, so the aircraft is stable. At the most aft center of gravity position, a typical transport aircraft has a positive static margin of around 5 to 10%. Current fighters typically have positive static margin of about 5%, but new fighters such as F-16 are being designed with relaxed static stability RSS, in which a negative static margin is coupled with a computerized flight control system that deflects the elevator to provide artificial stability, and this also reduces trim drag greatly. Aerodynamic center, a critical term XACW, is the location of the wing aerodynamic center. Wing tail lift. The lift coefficient of wing is given by the equation CL is equal to CL alpha into alpha plus IW minus alpha naught L. The lift coefficient for the wing is given by the equation CLH is equal to CL alpha H into alpha plus IH minus epsilon minus alpha naught L H, where alpha naught L is the angle of attack for zero lift and epsilon is downwash effect. Wing pitching moment. The wing pitching moment about the aerodynamic center is largely determined by the airfoil pitching moment. For a highly swept wing, the center of pressure of the flap lift increment can be ahead of the center of gravity, creating a positive moment increment. This reduces the download required by the tail. Downwash and upwash. Ahead of the wing, the air is subsonic flight is pulled upwards by the pressures about the wing. This upwash pushes upwards on the fuselage forebody and also turns the flow prior to reaching a propeller or inlet location ahead of the wing. Behind the wing, the flow has an initial downward direction, theoretically equal to the wing angle of attack. This downward angle diminishes aft of the wing to a value of approximately half the wing angle of attack at the tail of a typical aircraft. Also, the downwash varies across the span and approaches zero near the wingtip. Fuselage and nacelle pitching moment. The pitching moment contributions of the fuselage and nacelle can be approximated by Cn alpha fuselage is equal to Kf into Wf square into Lf by Csw per degree, where Wf is the maximum width of the fuselage or nacelle and Lf is the length of the fuselage. Thrust effects. Thrust has three effects: the direct moment of the thrust, That is, it is simply the thrust times the moment arm about the center of gravity. Second one, the propeller or inlet normal force due to turning of the air. So the normal force due to the turning of the air at an inlet front face FP can be calculated from momentum considerations. This normal force equals the mass flow into the inlet times the change in vertical velocity. Third one, the influence of the prop wash or jet induced flows upon the tail, wing, and aft fuselage. So the prop wash affects the downwash seen by the horizontal tail and reduces the tail's effectiveness. Trim analysis. Trim requires that the total moment about the center of gravity equals to zero. This we have discussed in the previous slide. For the graphical solution, arbitrarily assumed aircraft angle of attack and elevator deflection angle delta E are used to calculate the total pitching moment coefficient CMCG. The equation is used to determine the tail lift term, that is CLH, that's equal to CL alpha H into alpha plus IW into 1 minus dou epsilon by dou alpha plus IH minus IW minus alpha naught LH. For the arbitrary assumed angle of attack and elevator deflection, the total lift coefficient CL total can be estimated using the equation CL alpha into alpha plus IW plus eta H into SH by SW into CLH. The total induced drag, including trim drag effects, can be calculated at the trim angle of attack and elevator deflection angle using the equation CDI trimmed is equal to K into CL alpha into alpha plus IW whole square plus eta H SH by SW KH into CLH square. Lateral directional stability. In many ways, the lateral directional analysis resembles the longitudinal analysis. However, the lateral directional analysis really embraces two closely coupled analyses, the yaw and the roll. The yaw deals with directional and the roll deals with lateral. It is important to realize that both are driven by the yaw angle beta and that the roll angle actually has no direct effect upon any of the momentums. Furthermore, the deflections of either rudder or aileron will produce moments in both yaw and roll. Yaw and roll moment equation and its trim. So the figure shows the major contributors to yawing moment N and rolling moment L. Yaw and roll are positive to the right. Yawing. The major yawing moment is due to the lateral lift of the vertical tail, denoted by FV. Rudder deflection acts as a flap to increase the lateral lift of the vertical tail. A vertical tail immersed in the prop wash experiences an additional force. The air in the prop wash has a rotational component caused by the propeller and in the same direction that the propeller rotates. A propeller usually rotates clockwise when seen from behind. For a vertical tail above the fuselage, the prop wash rotational component causes the angle of side slip at the tail to become more negative, thus yawing the nose of the aircraft to the lift, called as P effect. The wing yawing moment can be visualized as an increase in drag on the side of the wing that is more nearly perpendicular to the oncoming flow. Another wing yawing moment occurs with aileron deflection. The wing with increased lift due to aileron deflection has more induced drag. So the yawing moment is in the opposite direction of the rolling moment due to the aileron deflection. This is known as adverse law. The three effects by the engine upon lateral moments, which is of same as longitudinal moments, are direct thrust, which is in yaw, the thrust is balanced unless an engine fails. Second one, normal force. The inlet front face or propeller disc has the same normal force term discussed for longitudinal stability. That is, the normal force due to the turning of the air at an inlet front face FP can be calculated from momentum considerations. Third one, prop wash or jet induced flow field effects. The prop wash or jet induced flow field effects are generally negligible in yaw unless the vertical tail is in the prop wash or near to the jet exhaust. Next, the concept of rolling. In rolling, the major influence is the wing rolling moment due to dihedral effect. This rolling moment tends to keep the aircraft level because it side slips downwards whenever a roll is introduced. The dihedral effect rolls the aircraft away from the side slip direction. The ailerons, the primary roll control device, operate by increasing lift on one wing and reducing it on the other. The aileron deflection delta A is defined as the average of the left and right aileron deflections, the directions shown. Spoilers. Spoilers are an alternative roll control device. These are plates that rise up from the top of the wing, usually just aft of the maximum thickness point. This disturbs the airflow and spoils the lift, dropping the wing on that side. The vertical tail contributes positively to the roll stability because it is above center of gravity. The yaw and roll moment are summed the following equation for a twin engine aircraft with one engine out. So the equation N is for yawing and the equation L is for rolling. Yawing force acted upon for yawing, that is N, and force acted upon for rolling is L. The yaw and roll moment equations are expressed in coefficient form by dividing through by QSWB to the previous equation which we have seen in the previous slide. So the yaw equation is given by the coefficient of yawing force Cn, and for rolling moment the equation is coefficients of rolling, which is Cl. So Cn is equal to N by QSWB and Cl is equal to L by QSWB, which gives you the equation for yaw and roll moment. Lateral trim analysis. Engine out case is the vertical tail with rudder deflected must produce sufficient yawing moment to keep the aircraft at zero angle at side slip, at takeoff speed with one engine out, and at aftmost center of gravity location. Second one, crosswind landing case, which is the aircraft must be able to operate in crosswinds equal to 20% of the takeoff speed. Third one, brute force method. It increases the vertical tail size but adverse effect on aircraft weight and drag. Last one, rudder effectiveness. Under this rudder cord, span, double hinged rudder, and all moving vertical tail can be used to increase the rudder effectiveness. Static lateral directional stability. The yaw and pitching moment derivatives with respect to side slip is given by C and beta, given by the equation C and beta. So the power of C and beta, as you can see, is simply the sum of wing, fuselage, and vertical tail contributions. Wing lateral directional derivatives depends on dihedral effect. So the rolling moment due to side slip or dihedral effect is proportional to the dihedral angle, but also includes the effects of sweep and wing vertical position on the fuselage. Fuselage and nacelle lateral directional derivatives. The yawing moment due to side slip is expressed in the equation as a function of fuselage or nacelle volume, depth, and width. The fuselage contribution to roll is usually negligible except for its influence upon wing effective dihedral. So the coefficient C and beta fuselage is equal to minus 1.3 volume by SWB into dF by WF. Aileron sizing. The aileron control power can be approximated using a strip method. The portion of the wing having the aileron is broken into strip as shown in the figure. The lift increment due to aileron deflection is estimated as a flap effect. This lift increment is then multiplied by the strip's moment arm from the aircraft center line Y1. Remember to reduce the aileron effectiveness about 15% if the hinge gap is not sealed. The yawing moment due to aileron deflection depends upon the spanwise distribution of induced drag with aileron deflection. This varies with the wing lift coefficient as well as the aileron deflection. Yawing moment due to aileron deflection can be approximated by the second equation, CL in the wing lift coefficient. Stick-free stability. The precedent analysis has assumed that control surfaces are rigidly held to the desired deflection. This stick fixed assumption is responsible for most modern fighters and large transports that employ fully powered flight control systems. Many smaller aircraft use purely manual or simply boosted control systems in which the air loads upon the control surfaces cause them to change deflection angle as the angles of attack and side slip vary. Such a case requires a stick-free stability analysis. Typically, the stick-free neutral point is about 2 to 5% ahead of the stick-fixed neutral point. Stick-free directional stability is also reduced as a result of rudder float. Effects of flexibility. First one, longitudinal bending. If the fuselage is flexible in longitudinal bending, the horizontal tail incidence angle will reduce when the aircraft angle of attack is increased. Second one, swept flexible wing. It will deflect such that the wingtips have a reduced angle of attack compared to the rigid aircraft. Third one, dynamic pressure. At high dynamic pressures, the ailerons will produce torsional moments on the wing that twist it in the opposite direction from the aileron deflection. Last one, a stiffer aircraft such as a fighter with a low wing aspect ratio and a short fuselage will have less impact on its static stability derivatives due to flexibility. Dynamic stability. Dynamic stability concerns the motion of the aircraft, which involves inertia forces and the damping forces. Inertia forces derive from the tendency of mass to resist accelerations. The mass for rotational accelerations is represented by mass moment of inertia terms denoted by capital I. Mass moment of inertia describes a body's resistance to rotational accelerations and is calculated by integrating the products of mass elements and the square of their distance from the reference axis. For aircraft dynamic analysis, the mass moment of inertia about the three principal axes must be determined. Ixx about the roll axis is given by b square w rx square divided by 4g. Iyy about the pitch axis is given by L square W Ry square by 4 into G. And finally Izz about the yaw axis is given by B plus L by 2 whole square into W Rz square by 4 into G. Damping forces. Aerodynamic damping forces resist motion. The rotational damping forces are proportional to the pitch rate Q, Q dash, roll rate P, and yaw rate R. These damping forces arise because of a change in effective angle of attack due to the rotational motion as shown in the figure from the lift on the horizontal tail during a steady pitch up and for the lift on a segment of the wing during a steady roll. The lateral lift on the vertical tail in a steady yawing motion would change similarly to the horizontal tail. The equations provide first order estimates of the pitch and yaw damping derivatives, that is, coefficients CMQ dash is given by the equation which is shown in the screen and CNR which is the second equation given in this shown in the screen. Next is aircraft dynamic characteristics. The lateral equations of the motion yield Three solutions to a yaw disturbance. First one, damped direct convergence. Second one, the spiral divergence mode, which involves an increasing bank angle with the aircraft turning tighter and tighter under control is lost. Third one, Dutch roll, which is short period oscillation, sees the aircraft waddle from side to side, exchanging yaw and roll. So in this session we have discussed about introduction to stability and control, and then different coordinate systems, body axis and wind axis system, longitudinal static stability and control, and concepts involving longitudinal static stability and control, pitching moment, and then we have studied lateral directional static stability and control, which involves yaw and roll moment, and then we have studied about aileron sizing, and then stick free stability, then effects of flexibility on stability, and then we have studied about the concept of dynamic stability, which involves inertial force and damping forces, and then finally we have studied about aircraft dynamic characteristics. So if you have any suggestions, doubts, clarifications, comment below. Subscribe to the channel Professor Srinidhi Kukila. Thank you.